Okay, so I guess we'll get started. So this is the first PCB workshop. We're going to be covering basically how you start a PCB, namely when you're designing the schematic, which describes what the PCB is going to actually do. So start with what is a PCB to begin with. It stands for printed circuit board. Basically, it's a base that holds and connects all of your components you want. It lets you make reliable connections, make it much easier to assemble than if you had a bunch of wires that you were soldering between pins and stuff like that. And you can make hundreds of wires really, really easily because you just click on a mouse as opposed to trying to like strip, tin, and solder a ton of little wires like that. So you can see a couple different boards I have here that have been for iRobotics or my own personal projects. They're just basically a flat board that has a bunch of copper connections that connect all these like silver looking pads that you solder the components down to. So they're made up of layers. So you have copper layers that are actually carrying the electrical current, and that's the traces that are inside the board on top of the board. And then there's the silvery solder pads where you actually solder the components down to. And then inside is the substrate layers, which is generally like a fiberglass or something. And that's what actually makes the board like have thickness, basically. Like, don't know how you can see that, but there's kind of like a translucent color. That's the fiberglass that's actually holding the board together. So that's what a PCB is. Basically, it makes making more complicated electrical circuits much easier to implement because you don't have to spend the time trying to make it all the connections yourself. You can just assume that they will work when you design a board that meets all these requirements, and then you can be pretty sure it'll work when you get it manufactured. So what can you do? Basically, there's like two sorts of PCBs that I see. There's like a carrier board and a functional board, where I have examples of both on the top right. There's the carrier board where you basically have a bunch of connectors where you can plug in modules to connect them all together. So you can see there's like a Raspberry Pi on there. There's an ESP32 board. There's a voltage regulator. They all just plug right into the board, and the carrier board just does all the connections between those modules for you. And there's not really a ton of electrical design. You're not making a bunch of circuits. It's mostly just allowing you to make connections between these modules you can buy online, which makes it a lot cleaner than using something like a breadboard and little DuPont wires. It looks more professional. It holds them a bit better. And you can generally get it a lot more compact when you can do something like this. And if you have something that's broken, you can easily pull out a module, plug in a replacement in, and it'll just work to begin with right there. Instead of with a breadboard or something, you might have to figure out what's broken, somehow pull the component out without messing up all the wires, and then plug a new one in, and then you're going to have to basically check and make sure all your little DuPont wires are still in the right place. So it makes it a lot more robust and kind of easy to figure out where everything goes, and easy to like maintain and replace and fix things or add things on if you need them to. And then the other type is what I'm calling a functional board. Basically, this is one that has actual circuitry on it and it has some sort of purpose. So it's mostly made up of active components. So you have like integrated circuits, like you have a microcontroller, you have a voltage regulator, something like that, and then passives like resistors, capacitors, that sort of thing. And so like the next bullet point is functionally a unit-based design. So what I kind of mean by that is it has a bunch of little sub-circuits that kind of work together all to accomplish one goal. So each little unit does their own thing, and then all together, all the units work to have some sort of purpose. So for example, in the bottom right there is the board for the PackBot. So for example, this is a motor driver board. It allows the robot to drive around and move consistent distances and at consistent velocities and such. So the way this board was designed is there's some inputs, which is like serial data coming from the Raspberry Pi that is controlling the robot. and then the output is the wheel needs to spin at a certain speed or move a certain distance and so forth. So the way it's designed is there's like a microcontroller sub-circuit that does all the processing. There's a motor driver sub-circuit that actually powers the motor. There's an encoder sub-circuit which detects where the motor is and where the wheel is so we can know exactly how much we've moved and stuff like that. And so each of those are like separate units, but then all together they communicate to have the encoder tell the microcontroller how to tell the motor driver to have the motor move the right amount we need so that it can all fulfill this input of serial data to tell it to move, and we can have the output move exactly like we want it to. Does that make sense? I know it's kind of a weird topic. Feel free to unmute or ask questions in chat at any time. Okay, I guess we'll move forward then. So these are the two things that you generally see boards doing. And so where do you start once you have like decided you want to do a PCB? Basically, you have to figure out your system level design. Like, are you planning on using off-the-shelf modules from like Adafruit or SparkFun or something like that? Or are you going to be designing your own functional boards, as I'm calling them, which are basically those modules? And if you are going to make your own modules, you better have a good reason to, because it's a lot easier to buy something you know will work from Adafruit or SparkFun or something like that, as opposed to making it yourself. Other than getting to make it yourself is kind of fun, it just might prolong how long it takes to build your robot or whatever. So make sure you have a good reason, whether that's I want to try to do it, or I want to try to make my own version of what they have or tweak some things so that it acts a little bit differently than something I can already buy. Just something like that. Keep that in mind, that modules are, it's not a cop-out or anything. They work great, that there's a reason that I built this PackBot board that is a carrier board, because it worked really nicely. It was easy to replace, easy to maintain, and didn't take a huge amount of design work to figure out everything, because there's not all these sub-circuits. It's mostly just connecting wires together for you. And so after you kind of figured out if you're going to be doing a functional or a carrier board, like mentioned on the last slide, you're going to break your system up into either multiple PCBs, multiple blocks on a single PCB, or however you want to kind of lay everything out. So for example, the last one on the PackBot board, the way everything was set up is in the bottom right. This board does all of the motor driving stuff. And then there's another board that does all of the Raspberry Pi path planning stuff. So we split the two tasks up into two different PCBs to make it so that one was just dedicated to driving, one was dedicated to deciding what to do exactly. And so that split up basically what circuits need to be on which board, and makes it a lot easier to test, to design it, to debug it, all that, because they're just separate things you can look at separately. You don't need to put it all together and say, it doesn't work, what's wrong, and then try to debug everything all at once. You can split your work up there. So in the case that you do multiple PCBs, you have to figure out how are they going to communicate? Is their power going to be transferred? What sort of communication is there going to be? Is it going to be some sort of serial, I2C, SPI? What sort of communication do you want? And so once you figure out basically how these are going to communicate, again, check, can you buy something that'll do this for you? And if so, maybe consider working with that standard, whatever they use for communication or power or anything. And then you could just cut half of your work away and just plug in a module that you know will work and just match that, which again goes back to the carrier board. So you can have a carrier board which has some circuitry on it that does stuff like a microcontroller, but you can kind of move back and forth on the spectrum to cut away how much time you have to put in. If you want to just focus on the microcontroller and then just buy some sort of motor driver and plug it in, this is kind of the point where you'd figure out what sort of communication do I need to have between this module and my functional board, and just something like that. And the same thing applies to these blocks on a single PCB. So again, these blocks are going to do certain things. Like I mentioned for the PACBOT board, there's the microcontroller sub-circuit, there's the motor driver, and you need to figure out how are they going to communicate, how is power going to be handled between them. And it's the exact same situation as if you had multiple PCBs, because you can look at them as this is one little unit, it does its own thing, this is another unit, it does its own thing, and then you need to figure out how to get them to talk to each other or work together. And so after you've figured out kind of generally what your system is going to look like, if it's going to be multiple PCBs, all one big one, are you using modules or not, all that sort of stuff, basically I'd recommend just drawing out a block diagram of the system. So you'd have basically like each PCB would be its own block, each little sub-circuit underneath it or module would be its own little block inside of that, and you'd say, how is everything connected? Is it connected with I2C, SPI, serial, whatever you decide to use there. And then again with the power, so is this getting 12 volts? Is it getting 5 volts? Is it getting 30 volts? Whatever it might be, just kind of draw it all out either with like Google Drawings, Paint, on like the program, draw it out in paper. It works great well too. Anything you can do to kind of get a visualization of how everything works together and make sure that you're not like missing any connections, so you have a good idea of what all needs to be done once you actually do start the schematic design. And then once you've done that block diagram, you need to do a high-level diagram, which is basically putting all these blocks together. So you'd have one for like the PACBOT PCB for the motor driver, one for the control unit, the thing that's deciding which way to go, how far to move. And then you need to put both of those two blocks to say, okay, so these are two that are going to connect together somehow. And then you need to say, okay, I'm going to use this communication between them. This is how power is going to go between them and stuff like that. Doing the same thing just on another step up, so you know like how everything's going to communicate when you do make two separate boards, or if you make two separate blocks, whatever. And just make sure that you're not accidentally forgetting something that's connecting, or forgetting like, oh, I forgot that this needs to communicate, so that the motor driver knows how the other motor driver is moving or something like that, because it's really easy to forget one little wire when you're drawing out all these different things. So drawing it out physically or on a computer works really well for looking at it and just visually seeing, am I missing anything at this point? Okay. Do you guys have any questions about this, kind of where to start, how to get started with figuring out what to do for in terms of your PCB? We'll be going through an example a bit later as well, so might make more sense then. Okay, so next step would be to actually start the schematic design. So once you've created a high-level diagram of the PCB you want to make, so you're going to start creating the schematic, which defines how everything is connected electrically. So it tells the software what connections need to be made in the PCB, because it'll take your schematic and it'll take your board and compare them and say, oh, you're missing this wire you had in the schematic when you do the board layout, and it'll tell you like, are you forgetting something? And it'll help make sure that your board will work the first time when you get it manufactured. So the first step is basically going to be finding active components. And by that, I mean finding the things like integrated circuits, microcontroller, anything like that, voltage regulator, something that's physically doing something in the circuit, not just a resistor or capacitor or something like that. And so there's a couple different ways to find these. One of my favorites is probably to find development boards online, either from like Adafruit or SparkFun, or directly from whatever manufacturer, because they're very helpful for finding part numbers for things that you want. So it's really easy to find something like a PWM servo driver. You can just Google that and you'll find a bunch of different breakout boards, development boards. And then from there you can say, oh, this one looks good. And then you can just take the part number from that board and then just use it in your design. If you don't want to use that pre-made module, you can just take the part number off of it and reuse it in your own. And so if you don't want to do something like that, or you're looking for something more specific, then something you can find at like SparkFun or Adafruit, You can use DigiKey, Mouser, anything like that to find components with like exact values you want. This works really well for finding like voltage regulators. There's a ton of different options for filtering, like what output voltage, what input voltage can it have, and it can basically find you the exact part that you want. I can go through that a bit later at the end after this slide and show you kind of how that works, but it helps you narrow down these tens of thousands of possible chips down to like a couple that you might be interested in, and then you can kind of manually compare the last couple characteristics to see what would be best for your design. If you need higher voltages or lower voltages or don't really care, anything will work. And so once you've kind of figured out what part numbers you want, you need to add all those components into your schematic. And again, I'll go over this at the end of the slide. And so you can find these parts for Eagle, basically, like you can load the library into Eagle and it'll just give you the footprint. It'll give you the schematic symbol just right there. You can find it on DigiKey. They normally have like a little ECAD download link and you can just download it directly and load it in, or you can Google it. So typically, if you just like Google the part number space Eagle, you'll find plenty of websites that you can download the part number or the part footprint for and the symbol for, and it'll be loaded into Eagle, and then you can just place it in and it'll update everywhere else. So when you put it in the schematic, it'll be able to, you can connect to it and you can set your circuit up that way. So do you guys have any questions before I get into a little bit of a walkthrough for this first part? Again, feel free to post any questions in the chat if you have them while we're going through this. But I guess we'll start. So basically what I'm going to do is we're going to make a like PWM driver board. So if you wanted to control a bunch of servos with one microcontroller, this is what you'd need. So first thing, you need Eagle. So if you have this installed, feel free to follow along if you want. Otherwise, I'll send out the recording and then all the design files I make afterwards. So first, we need to figure out what component we want. So going back to this, I'm going to look for a development board because, again, that's one of my favorite ways of finding parts. It's really easy to figure out what most people work with, not to mention when you use something that's from a development board, you can probably find open source code for it that you can just copy and paste and use in your robot, and then you don't need to write a whole library of how do I interface with this device. So we'll just search PWM servo driver develop. Sure. So like I mentioned, Adafruit shows up a lot, so does SparkFun. So we'll just look at this first one, 16 channel, 12-bit PWM. So this is a pretty basic board, it looks like. There's just like the one IC and some resistors on here. So you can see it uses this PCA 9685 chip. So we'll just take that part number and then we can just Google it basically. And here it looks like it's an NXP part. So we can look at the data sheet, kind of see exactly what it does, if there's any features we might need beyond what this has. But so PWM, it's an LED controller. LED controller doesn't necessarily mean anything. It's just it can generate a voltage. I've already looked through this, so I know this is the part I was planning on using. But basically this, you can look through data sheets to find what you want. But basically the general description, the first bit that it tells you about it, it's an I2C LED channel controller optimized for whatever backlighting applications, whatever. It has a 12-bit resolution PWM controller. So that's exactly what you need for driving servos. You just need a PWM signal that you can, that's at a fixed frequency for most servos. You can use that. So we'll just take this and we'll use this part. So either you can go from the data sheet and make your own footprint for it and your own symbol for it based on, probably towards the end, they have footprints for all of these, which have dimensions that you're going to need to basically model after, though that takes quite a long time. So like you could take this page here of the data sheet, copy in all these numbers and generate a footprint, or you can go to someplace like DigiKey, which sells the components. You can just search for the part number. We'll find, here's the LED drivers. We don't need a development board, though you can buy one there. Probably the Adafruit option anyway. And so here are the couple options they give you. So there's this QFN part, which are a bit harder to solder. Oh, yeah, so Kurt just mentioned in the chat, there's an Eagle package generator. So that's kind of what I was hinting at with the data sheet. You can read those numbers off the table and enter them into Eagle, and it'll generate the footprint for you. So you don't need to always manually design it, but this way that I'm about to show you is significantly easier. But yeah, so you have QFN packages, which are generally higher power. They're way harder to solder though, because there's no pins on them. They're just these little like flat pads that get soldered down. You need like a reflow station or a hot air station to solder them really well. So there's this other option, which is a TSSOP, but basically you can just look at the picture. It has pins, and that's generally an easy part to solder because you can use a regular soldering iron and just make sure there's no shorts. So we'll want to take one of these three. And so the first thing, once you've like picked out, you want one of these three here, they kind of look exactly the same. They have a slightly different part number. And basically what that comes down to is like this one on the bottom is rated for automotive. It has an AEC Q100 rating, and then what package it comes in. So generally you don't need to worry about the automotive rating unless you're like making something that's going to be in like a combat or something. Probably don't need to worry about it. This is more if you're making an actual automobile that needs to work for like years in really bad conditions. So you can pretty much ignore that. And then the packaging options are basically you want to look for something like a cut tape or tube here, because that is generally ones you can buy in like quantities of one or something like that, which you can see here, minimum quantity of one. If you wanted to buy it in bulk, you have to buy 220 of these, which not good when you're making one-off things for robots or something like that. So generally I filter by cut tape up here. So if you just say, I want it to be cut tape, it'll just filter out anything that's not available that way. And so now we're looking at these two. You can either spend 226 and not have the rating, or 238 and have the automotive rating. They're the exact same part otherwise. So we'll just look at this one. And so here they have the data sheet here. They have environmental information, design resources, tons of information here. All of the characteristics, like how many outputs it has, voltage supply it can work on, current it can drive. And this changes for what type of component it is. But the important thing is this ECAD or EDA CAD models. That's basically the library you can download and load into Eagle, and then you can just put it in your schematic without having to design the footprint and the symbol yourself. So we'll go with this Ultra Librarian because Ultra Librarian is basically made by DigiKey. It's a bit more professional than the other options. So here's the symbol that you'd get. Here's the footprint of the actual device, and some even have this 3D model, which shows like what it'll actually look like, which you can use if you want to make a full 3D reconstruction of your board with all the components on there. So we'll download it. We want Eagle. We'll say this only option. We're working for version 6. Need to log in, so you can make an account. It's professional. They don't spam you or anything. And then you can go through this. You're downloading sequential or functional. Basically, if you do sequential, it'll just be the pin numbers going around. if you do functional, it'll put like all the power stuff in one block. So like the V in, the ground pin will be there, and then all your other connections will be in another block. But sequential is fine for now. So we'll say we're not a robot and download. Okay. So once that's ready, I've made a folder here so we can just take this zip file we downloaded, and then we need to turn this into a library. So they give you instructions here. So it'll walk you through how to do it if you forget, but basically you just need to go through and it gives you a script file that Eagle can turn into a library. So if you just copy this file out to someplace that's not in the zip folder. So here we'll say this is the PCA 9685. So then we need to run that. So the way I generally do it is we go to Eagle, the main control panel. When you open it, file, new, we're making a library. And then we're going to go to file, execute script, or you could click this script button up here, SCR. And it's not in my example scripts folder. Thanks, Kurt. I forgot to share that. Okay, can you guys see that now? I'll go through this stuff again. Okay, so yeah, basically you'd open up the Eagle control panel, which is just like the Eagle program. When you click on the icon, you can go to file, new, we're going to make a library. And then you can either click execute script here or in file, execute script. They're both the same thing. And since we have this script file here, not in this example scripts lib folder, we'll browse. We'll go to that folder wherever it is. And then we'll open this script file that we downloaded, open it, and give it a couple seconds because it basically generates all of the footprints, generates all the symbols, and then puts them all together and gives you a library that has everything all put together. So you can see here's the symbol that the web page showed and the footprint, and it's connected all of the pins saying, this is the schematic letter number here, whatever the name of the pin is, and here's the number of the pad in the actual footprint on the right here. So now we can just save this library, and I'm just going to put it in the folder for the workshop. So PCA 9685. Save that. We can close this. And now at this point, now that we have the library, we can delete the thing we downloaded in the script file. We don't need that anymore. So now we have the library that has this component. So at this point, we've gone through the first step here of finding the components we want. So these are all the active components we really need for this. We could add something more like MOSFETs for reverse polarity production, stuff like that. But for basic PWM driver board, all you have to do is get that. And at this point, then we can start the schematic. So again, in Eagle control panel, we'll go to file, new, make a schematic. Okay, that's fine. And so this is what it looks like when you open it up. It's completely blank and boring. So at this point, to use that library we downloaded and then generated, we're going to go up to the library button, open library manager. Give it a second. And then this window is kind of weird the way it works, but basically InDesign is auto-generated, so you can't like change anything here. But in use, these are all the libraries that are installed on Eagle right now, but ours is not in there. This is like the provided ones from Eagle already. So if you go to browse though here, and then go to the library we just created, You can see there's the PCA 9685 library. We can open that, give it a second, and then we can just close out of this. And at this point, Eagle now is aware that that library exists and we can add it into our schematic. So if we add part with this plus part symbol, you can click on that. And then all of these are, it's a lot of libraries, and search does not really work. It's a weird search. So generally I just look based on, oh, okay. Yes, Library Manager is very helpful, Kurt. It lets you add a bunch of things in basically all at once. Yeah, Eagle Search is a joke. That's very true. The search bar is very weird. The way it searches, it like looks for like text in this box, which doesn't ever match up with text of like the name of components. So basically I ignore the search bar. And one thing you can do is if you're like selected one of these, if you press like a letter key, it'll jump to that area. So I pressed P, and then there's the library we're looking for, the PCA 9685. We can click the arrow to open it up. Here's the actual part number for the TSSOP version. And then there's 3 options. Basically, they're meant for if you're doing like wave soldering or reflow soldering or whatever. But the easiest one if you're doing like hand soldering with like just a regular soldering iron is to use the reflow one, which is this -M. So if you look at the footprint, when I switch back and forth between these, the M pads are longer, so it's easier to like take a soldering iron and like rip away if there's any solder joints. It'll like split it up a lot better. So we'll use that one. So we'll click OK. And it didn't like that for some reason, so we'll click OK again. And then we have the part here, so we can place it down wherever. We can click escape a couple times to get out of that. And then this is our component. It has all the pins we had seen on the actual schematic or on the device here. So each of these little pins is represented as one of these little traces that you can connect to in the schematic. And so at this point, we're through this whole thing. We put all the active components we need in the schematic. And so at this point, we'll jump back to the presentation and go forward a little bit more. So do you guys have any questions about this whole starting schematic design? How do you find parts and put them in Eagle, anything like that? Again, feel free to post in chat or unmute, whatever you want. Okay, well, again, after all this, feel free to send me messages on Discord. If you want to send me an email, that's fine too. I'd be happy to explain things, help remind you of anything I've talked about, or help you figure out weird issues, because Eagle is very much rapid development and things change and act weird all the time, as Kurt can attest to. So moving on, now that we've had all these active components in the schematic, we've imported the libraries, put them all in. Next would be to break up the page by a high-level block. So this doesn't really apply to our walkthrough because it's a pretty simple board. There's only one block, really. It's just the IC that takes I2C input and gives you a bunch of PWM outputs. But this would be the point where if you have like a bunch of voltage regulators and then you have like a motor driver and a microcontroller, you'd want to put each of those things on separate pages just to make your schematic cleaner and easier to read. So it's not just everything all shoved into one page. So I'll show you an example of this a bit later after this slide. So next, you're going to be adding all the other components to the schematic. So this is adding in the resistors, capacitors. If you need like connectors or something, this is when you'd add them in. And again, if you know what you're doing, go ahead, just feel free to just draw it all out. But most people don't know exactly how every chip should be implemented off the top of their head. So look for the term like application circuit or if you got this off of a development board, see if they have published schematics or anything like that, which will give you an idea of how to actually connect the device up to everything else it needs. So if it needs a resistor, pulling it up to 5 volts or pulling it down to ground or whatever it needs like that, you can find that all on this application circuit within the datasheet, or on development boards you can take help from in terms of their schematic if they've released it. And then if you're trying to do something more complicated or like an analog realm, circuit simulation can be really helpful. So there's plenty of websites you can find for doing circuit simulation. You can use free tools like PSpice, LTSpice, PSpice for TI, tons of different tools that'll simulate everything for you and have tons of parts built in. And you can probably find the like active components you're using in some sort of library that you can load into these programs, and you can simulate how they behave. So you can generally avoid that just by looking at the application circuit, especially if you're working in like digital realm. So you're working with like servos, PWM, stuff like that. If you're working more with analog stuff, you might need to get into the simulation type of thing, but generally you can avoid it, especially if you're not making like a functional board that is meant for like analog signals or something like that. And so once you've got all these components put in the schematic and you have everything you need, you wire them all up using the wiring tool. And so you're creating these nets, they're called, which is basically, it's like a network. So whenever you make a trace with the wiring tool, it says this pin needs to be connected to this pin for sure, no matter what, absolutely. And then so it makes a net between those two pins. If you say that, oh, this pin also needs to be connected to this other pin, it'll make a net between those two, and then it'll form them all into one net. So it's like they're all connected to each other in the board when you actually make all the wires. You have the manufacturer have it skim through the chip errata. Yep, that's a very good point. Sometimes manufacturers release chips that have like weird issues. They don't work exactly like the datasheet says they will. So sometimes they release errata, which would be like right beneath the datasheet download link. And it'd basically say, hey, this didn't work. You need a pull-up resistor on this pin to make it work like it should, or something like that. So you can generally find those sorts of issues if you're going off of like a development board, but you might not find them if you're going strictly off of the application circuit in the data sheet. So just check out if there's anything that's not acting like it should, especially if you're debugging, like, why is this not working? This is exactly what the application circuit says. Like, might want to check if there's any errata that's been released that says, hey, this thing doesn't work exactly like it's supposed to. So once you have made all these connections, like through making nets, basically, to say that they're all supposed to be connected ideally, and then when you make the board, it'll force you to follow those rules that you set for yourself. So we can walk through an example of that. So if we go back to our schematic here, so we only have this one page. If you wanted, say if you had like a voltage regulator, you can right click in this area, click new, and make a new sheet. So you can add a description, say voltage regulator, and then it'll basically make 2 sheets. When you print it out, if you print it out, there'll be 2 sheets, whatever. Get rid of that for now. We'll name this one as PWM driver. And then one thing I generally do, which I get into a bit later in the presentation, jumping ahead a bit just to make sure we don't have any issues later. If you go to this add part button, you can look up frame, which for some reason works in search. Don't ask me why it works, why it doesn't work, but if you search frame and look at one of these, so we'll take this letter frame A, paper A size frame, and then you can put this in your schematic. And then this is the actual size of like a piece of A4 letter paper, whatever. And it basically just constrains you so that it doesn't sprawl out over huge areas. And also if you want to print this out, it'll make sure everything fits nicely and doesn't get like super squished or made huge if you make your schematic like super tiny or laid out in a massive scale. So it's nice if you want, you can like actually rename these. You can say the title is, this is the PWM driver. The document number, date will auto update, sheet numbers will update. It's just a nice way to say like, hey, if you're working with somebody like, hey, there's a resistor on page sheet 1, B2, which corresponds to like this B2 area based on like the grid and column. There's something in there that has an issue. It makes it easy to like kind of lay everything out nicely. So that's jumping a little bit ahead, but so now we have this thing that we want to connect up, so we can look up the application circuit. So we'll go to the data sheet. And again, like I mentioned, if there was any errata, it would probably be right beneath this. This is just a brochure, but it'd be like PCEA 9685 errata, something like that. So if you can probably just search application circuit. That is not. Okay. So application circuits are kind of weird across different manufacturers. They do them differently. Some provide them, some don't. So I'm not sure if this one does or not. I don't use too many NXP parts. Kurt knows I use TI parts for basically everything. Yeah, I don't want to scroll through this, but you guys can look later if you want. But because we did get this off of a like development board here and named specifically from Adafruit or SparkFun, they release schematics for basically all of their boards. So if we go to their downloads page, here's their schematic. So we can grab the EagleCAD PCB files from GitHub. So here's the schematic file. You can download that and we'll open it up. And so this is a really good way to figure out how to implement like this chip, especially if you want to put this chip and something else on your board. You can say this sub-circuit or this block that is the motor, that is the PWM driver, is its own thing. This is how it gets implemented. And then your microcontroller block can be implemented separately on a different page or whatever. So this is how they've implemented it. So they have the chip in just a different footprint or a different symbol. It has a bit more information on it, but it's electrically the same thing. It has all these PWM pins. It has the address pins, I2C, and power. You can see the same thing. On this one, we have our address pins, PWM outputs, more PWM outputs, and then I2C and power and such like that. So basically, if we look at this one, we need a 10K resistor from output enable to ground. So we can add that in. So the way you'd find these other passive components is again using this add part button on the left here. We'll get rid of that. Wait for it to update. And there's this library that's provided by Eagle. RCL is the one I use for pretty much all of the resistors, capacitors, inductors is what it stands for. So if we go to like R-US, these are all the different resistors you could use. And so some of them are surface mount, so they're just pads like this, so they don't stick through the board. I think some of these are like through-hole resistors. If you want to do through-hole resistors as well, you can find ones that lay flat, some that lay vertically, whatever you want to do. For now, I'm just going to use the 1206 surface mount resistors because they're a pretty nice size. They're surface mount, which makes soldering a bit harder, but makes layout a lot easier. So we'll stick with this. We'll add it, and then we need to take this output enable pin to ground. So we'll put that over here, right next to the output enable pin. So next thing, we need VDD to be connected to, they call it VCC, but that's basically 3 volts or 5 volts, whichever you're using, basically. Like if you're using a microcontroller that's 5 volts, like an Arduino Mega or something like that, you want this to be 5 volts. If you're using something that is 3.3 volts, like an ESP32, you want it to be 3.3 volts. You can see even here, they say that it works in this whole range, and that same number is on the data sheet. So we can take this wire and just let it float for now, because there's nothing there that we need for connecting it to like 3.3 or 5 volts. There is this capacitor from this pin to ground, which is for bypass. So whenever you have an integrated circuit, you need a little bit of a capacitance right next to it. So if there's a current spike or something that needs more power, you can draw power from the capacitor because it's really close. It's like a little backup energy storage sort of thing. So we'll add a capacitor there. So again, we'll go to add part. Again, we can use RCL. We'll go to the C part. I generally use the EU version because the US version it looks like a polarized capacitor, but it's not. So I typically stick with the EU version just because, again, we can use the 1206 size, which is, again, a nice size for most purposes if you're doing surface mount stuff without needing to make it really tiny or anything. And so we'll take this and we'll add the wires a bit later, actually. So not a fan of 0603. 0603 are not great. I prefer 0805 for everything. Also, to everyone that is not very well versed in PCB design, these numbers that I'm saying are just a specifier for the size of a component. So 1206 versus, they're just dimensions of these components. So that's just how they're like referred to. This picture pops up. So actual size means meaningless on a picture. I don't know what they mean, but so you can see like 1206 here on the right is a bit longer, but you can go down to 0603 like Kurt mentioned, and it's very tiny by comparison. So it's just a bunch of different descriptors of how big it is. So the bigger the number, the bigger it is, generally easier it is to solder, but by it's bigger, you use more space in your PCB to fit it all. So yeah, basically you can pick that based on whatever you want, whatever is easiest to solder. If you need to fit in a small spot, maybe make it a bit smaller, but 1206 is pretty easy to solder. 0805 is my favorite. It's a nice size. It's not too small, but also is a lot smaller than a 1206. So other than those two, the resistor and capacitor we added, this is basically everything. We just have connections for ground, connections going out to all the PWM outputs. We have some connector inputs. So that's all that is connected directly to this. And so the next thing is showing what nets look like. So this trace kind of just ends here. And so it kind of looks like it doesn't connect anything, but the thing is, this is a net. You can see that it has this name here. And you can see as I move it around, it stays connected. So what that's telling Eagle is that this wire is connected to the net named PWM0. And if it sees any other wires that are on that net PWM0, they are like connected. So if we look around, here's PWM0. And so what this means to Eagle is that this pin 6 here with PWM0 is connected to this trace, to this resistor. And it's just a much cleaner way of doing it as opposed to like doing this. This just is horrendous. I hate that I'm even doing this. And like, it just makes it a lot easier to see where everything's going if you just name it rather than having a bunch of wires crisscrossing all over the place. So we will do the same thing for our board, or our schematic. So that's the name of those. And those all go to resistors, which we can add later once we have connectors. And so the next thing, if we go around here, all those PWMs, ground is close to ground. These address pins we can deal with later. External clock just goes to ground. SDA, SCL, which is the I2C communication pins, they go over here. So here's the same SDA, SCL net. And then you can see they have a 10K resistor pulling them up to VCC or whatever voltage we're working with. So we'll add that to ours. So since we already have a resistor here in the size, we can click the copy tool. Just click on the plus in the center of it, and then we can take, that's one we want. There's the other one we need. And we can move these around using the move tool over here whenever we need to, whatever. So that's basically all of the components we need, other than the connectors and the resistors for the servos, which are more of best practice because you don't know who's going to plug something weird into this. You don't want it to just burn up your chip. You don't necessarily need those 220 ohm resistors, but it's best practice. So I guess we'll add the pin connectors now. So if we go to add part again, and then we can go to a library called Pinhead, which again is something that they just provide. And we'll go to Pinhead 1x3. So this is for a 3x1. So if you have a servo, it has 3 wires generally. So we'll add this part. You can see it has the 3 pins like you had for a servo. And we'll just add a couple of these just for showing you how it works. And again, at this point, we'll use the copy tool. We can click on the resistor, and then we'll add a series resistor for the signal pins. Just again, best practice, why not? So at this point, now we have all of the active components put in, and then all of the other components, so the passive components. And so now we can use this wiring or net tool to make connections. So you can see when I go near a pin here, there's like a little circle. So if I click in that, I then have this wire, which I can connect to wherever. I can connect it all the way down here if I want. But we're going to connect it to here for the signal pin. And then you can do the same thing down here for all of these. And so that says this pin will connect directly to this resistor. And then this resistor will go somewhere. We'll add a little net for now, and then we'll name it a bit later. Plus, oh yeah, you're right. Wait, no, plus is on the middle, Kurt. The plus is definitely on the middle, so you plug it in backwards, it doesn't burn up. Anyway, yeah, so we'll do that. We'll take out ground here. Okay. And so we'll do the same thing for over here. So we'll get rid of this for now. We'll use the net tool, SCL, SDA. We need to have resistors pulling it up to our VDD or VCC, whatever you want to call it. And again, at this point, this is when it's nice to have a block diagram sitting next to you so you can see where all the connections need to go. So you know that SDA and SCL need to go out to some connector. So you need to add a part in for a connector there. You need to get power, so you have a connector for power, stuff like that, just to keep it all in mind when you're making connections. So we'll take all these and we'll connect them to VDD. And then you can see when I connect 2 nets here. So if you look at them with the eye, this is net N17 right now, and this is net N15. So they're different. But if you use this net tool and click them together, it'll generally auto form it, but after you've looked at them, it'll ask you which one you want to name it. So we'll just go with N17 for now. And then you see it puts this intersection bubble, which basically says that anything coming together at this point is all connected. So if there's anything like running underneath it, it'll connect it. So if you do something like this, I don't know why you would. This just looks weird, and I would avoid this at all costs because it looks like all of this is all connected, but it's not because it has no bubble. So if you use like the move tool, you can see that it's not actually connected, it just looks like it. So avoid like crisscrossing like super close together, give things space. But if you like accidentally did this and you want to connect it, there's this junction button, which will let you manually place a button, and then these are all connected again. So that's just a little tidbit. So these are the resistors pulling SDA and SCL up to VDD, and then we'll put like a little tail here to say that this is going to be connected to our VCC, whatever it is. And then we'll put the capacitor up here as well, because that capacitor needs to go from that VCC to ground whenever we add that. And then we have output enable, which needs to go connect down to ground. Okay. So at this point, we need to connect all these grounds to ground. So you can either use like a label tool, which will basically like let you give it a name. So right now it says its name is N16. You can say GND for ground or whatever you want to call it. You can do that, though it gets a bit time consuming to do that for every single ground thing. So I'll show you guys a little bit of a faster way of doing it. So if you go to part, if you just search ground, you can find a bunch of symbols which are ground. They do the same thing. So if you add them and connect it, see it's going to rename this thing from N16 to ground. And then if you do it over here too, it's going to rename it to ground. You do all these, again, it'll just name them all to ground when you connect them. And also, you guys can't hear this, but Eagle beeps a lot for no reason. So maybe mute whenever you're using Eagle, or turn Eagle sounds off because it gets annoying. So now these are all connected with this symbol. You didn't have to type it in or anything, but if you use the info inspect button and just click on one of these, you can see it's been named the net ground, and you can see this one is also named ground. So that means that all of these things that are connected to this ground symbol are going to be connected when you make the board itself. So next we need to name this one. So we need to connect this to 3.3 volts or 5 volts or whatever it is. We'll go with 5 volts just because we're going to use 5 volts for the servo anyway. So again, you can go here and you can go to like one of these libraries like supply 1, supply 2, for some reason they're named that. You can go scroll, find them. You can grab these like V+, VCC, whatever you want to use. And it does the exact same thing, except it's just named VCC. Generally, what I don't use this for the voltages just because it can get confusing, especially if you have 5 volts and 3.3 volts and anything in between. So normally for voltages like this, I do it kind of the manual way, which is I just use this label button. I select XREF. I don't know what XREF stands for, but it makes it look nice. And then if you click on it, it lets you add like a little tag, which shows the name. And then you can use the name tool right next to it to say, okay, I'm going to name this 5 volts. And so this whole net has been named 5 volts, and anywhere else I name a net 5 volts, it'll show up and you will connect to this too. So we need to connect all these to 5 volts as well. Cross-reference. Oh, that's a good point. I will show that feature as well. So just for the sake of showing that off, we'll say this is the connectors page. Sometimes would put connectors on a different page, but for a pretty simple circuit like this, I might not. Also control like X, C, V all works as normal, so you can like cut and paste. We'll add a frame again to make it look nice. And then we need to say that these are all going to be connected to 5 volts in the middle, because that's what a normal servo looks like. I'm going to change the size of the text so it's a bit smaller, and we'll put that in there. And you can just click on it, basically double click on it to put the name in, or put the label on, and then you can name it later. You give myself a little bit more space, just because the label will get bigger basically after you add a name and the cross-reference thing that Kurt is mentioning. So if I click on it with the name tool and say this is 5 volts, it'll warn me, hey, you're about to connect 2 different nets. Do you actually want to do this? Say yes. And so now you can see it's named, the net is named 5 volts, but it gets this designator reference thing. So it's on sheet 1 in 5B. So if we go to sheet 1 and we look at block 5B, you can see that right here in this block is this 5 volts tag it's referencing, and then it shows you the other way around. So in 2.3C, if we look at sheet 2.3, and then we look at part C, you can see that that is also in there. So it lets you kind of see where is all the stuff connected. It's not just like 5 volts is everywhere, go find it. It kind of points you in the right direction. And so we can do the same thing for all of these. And it beeps and warns you every single time, but then you can see they're all referencing the same 5 volt net that is at one point, sheet 1 in column 5, row B. And then we'll do the same thing for these. We'll put a little label on there. Also, if you right click, it rotates so you can make things look nice. So if you had labels coming out this way, you can do that, or right click, you can do this. Again, there's a lot of Eagle tutorials online already if you want to learn exactly how to like use the software, but again, like this is supposed to be more of a how do you do PCB design in general. So I'll leave Eagle tutorials up to the plethora online, or feel free to like DM me messages about it. So here we'll say this is PWM 0. We'll say this one is PWM 1, and so far. And then you can see that there's no like slash because it's not referenced on any other sheet. There's nothing on sheet 1 that is PWM 0. So we'll have to add that in a bit. So next we'll put that in. So you can see here's LED 0, 1, 2, and 3. We'll add labels, again, using right click to rotate the label so you can actually read it. And then we'll name all these. And now that it already exists, it's going to warn you. And then you can see it links up. It says on page 2, column 2, row C, there's a connection there, PWM 1, same thing, PWM 2, and PWM 3. So you can see these all connected. You can see they kind of changed their designators because they're showing the connection in a different row. One's in C, the other 3 are barely in D. So if you move this around, it'll update everything. If you want to put it in the center, something like that. You can see these all updated. And now we need to connect this chip to ground and everywhere that the Adafruit board had it. So you can see ground gets connected to ground, obviously. X clock gets connected to ground. So we'll do both of those. So VSS means ground, X clock can get connected to ground. This is getting a little unclean for what I like to do, but it's fine. So we'll just connect this into this ground that's there already. And then again, we can just use the copy tool to copy this ground, put it on there. So now we have X clock is connected to ground, VSS or pin 14 is connected to ground. And that's all of the pins that get directly connected to ground. So next we'll look at the address pins, which specify what address on I2C that this thing will respond to. So this is kind of specific to I2C, but you can connect these to 5 volts or 0 volts directly, or you can do something like what Adafruit's done, where there's some solder jumpers where you can use a soldering iron to basically select what pins get what voltage, and you can set the address that way. Again, here's the address calculation they show. Like if you have a 1 for A5 here, if it's soldered, it'll be a 1 and so on. You can do this sort of thing for making your board configurable if you want to have different functionality. So, but for the purposes of this, I'll just connect all of these to ground. So we're going to connect those. And again, this is kind of showing sometimes it merges them, sometimes it doesn't. But right now, this A1 is not connected to A0, but I want it to be. So I can use this junction bubble and force all of these to get connected. And so now I'll just take this and then I'll add this to ground, which will set the address bits to 0. Or you could put it to 5 volts, whatever you want to do. And then there's another one over here for A5. And again, this is getting a bit messy for my liking, but we'll just scooch this over a bit. The Eagle does not like that. So there. So now we have A0 to A5 is all grounded. We have SDA and SCL pulled up. We don't have a connection for any of the input signals like 5 volts ground, SDA, SCL yet. And we don't have any connectors for LED 4 and LED 15, though you could add them on. So at this point, pretty much everything is implemented for the chip. So now we just need connectors. So we'll go to our connectors page and we'll say, I want to use a 4-pin head connector, which will allow us to provide it the voltage it needs for all the servos, and it'll provide the connections for like SDA and SCL. And so again, you can rotate components labels by just right-clicking, so you can make things orient the way you want them to. So add that, add little wires coming out, and then you can name them using the label tool. And then they get their auto-generated name, and then you can say, this one's going to be 5 volts. This one is going to be ground. Or you could use the ground symbol, they're equivalent. So if you name it exactly GND, it'll be perfectly happy with that too. So there's that. We can change the name for this to be like SDA and SCL for I2C communication. And then we just have to go over here and name these wires here like they have connected here, where the wires directly connected to the PCA chip are named that net name. So we can add a name. We're going to name this, I think this one is SDA. We're going to connect it to SDA. It's warning us because they're 2 different net names right now. They'll eventually be the same. And you can kind of see this doesn't look very nice with the little tag thing. It doesn't fit. So you can change it to XREF off just to make it look a little bit nicer. It doesn't tell you where it's referencing, but it's reasonably self-explanatory when you have one like I2C bus. You can do this pretty much without any issues. So there's SDA, SCL, and then you can see this one's referencing that here. So that's basically everything you need for this driver. You could connect an I2C 2 wires up 5 volts and ground. this chip would get powered by 5 volts. We'd have the pull-ups. You'd have everything connected up and enables pulled to ground to enable everything. You'd have the address set with all 0 bits. You have your PWM outputs, which go out to your connector. You have your series resistors for the signals. You have 5 volts and ground provided each of your servos. And now this is basically the whole schematic done. At this point, you'd want to add resistor values using this value button. So you'd use like a 10K resistor or something like that for I squared C. You can just add that for both of those. Here they recommended a 10 microfarad, so I'm just going to do a UF capacitor. This one was a 10K resistor. And again, these values are for pull-ups are kind of random. Like anything over 1K is probably fine. It just needs to pull it to 3 volts or to ground whenever it's not being powered. So those values are fine. And then we'll just use the same 220 ohms as the Adafruit board had. So we'll just use the value tool here, click on the plus in the middle. You can see that's what you can actually click on. If you click over here, it doesn't do anything. You have to click on the plus itself. And that's the same for all these components. Like you have to click on the plus here to move it around. You can't click over here. So once all those are named, we have basically the entire schematic done. Normally I'd save it throughout. You might have seen that this popped up a couple times as I instinctively clicked Control S, but we'll save this as PWM driver.schematic to the folder. And then basically that's it. This is the schematic for everything. You can print it out if you want, highlight things, make sure everything's connected correctly. And so we've connected all these nets, set all the values we needed. So next would be to review the schematic. Like I mentioned, printing out the schematic is by far the easiest way to make sure you have everything working right and everything is connected right. So highlighters are extremely helpful. I have a set of highlighters that I got just for this because you can take like an application circuit on a piece of paper, your circuit, and like highlight over things as you like make sure that they're the same or they're correct and you're not missing anything. And just go over every single wire, making sure that they're all connected, they're named the same thing. If you have little XREF thing, make sure that they're connected to each other and it's not like, oh, I used a 0 instead of an O for some reason and it looks right to me, but it is separate, stuff like that, just to make sure that they're actually connected as far as Eagle's concerned. And then once you highlight all those, make sure they're all named correctly, they make all the right connections you want. Basically, your schematic is probably good as far as you can tell based on the application circuit. There is an ERC check in Eagle, which is a check you can run on your schematic to make sure everything is good. Though take that with a grain of salt, it gives you a lot of warnings and errors kind of arbitrarily, depending on where you get your libraries from that we downloaded from like DigiKey, or if you make your own. It gives you a lot of warnings if you don't use all of Eagle's features when you're making them. Like you can say this pin is for power, this pin is an output, this pin is an input, and if you don't obey those, it'll give you ERC errors when really there's no actual error. But again, Eagle doesn't know what you want or what you mean. Just check that the schematic manually looks good. It's what you're meaning, it's what the application circuit has, and you'll probably find a lot of the issues you might have ran into when you actually made the PCB. So I can show you an ERC check really quickly. So if you go back to our schematic, it's down here in the bottom left, electrical rule check. And then you can see there's some warnings. There's no, so consistency check is making sure that your board design, when you actually make the actual physical thing that'll be manufactured, and your schematic are like consistent, that they line up, that they match. There's no errors, which is like, if you use certain Eagle features, it can tell you this is not connected, this has to be connected, something like that. There's a couple of warnings, like these have no value. So The frame itself has no value, which is fine. There's no resistance value of a frame. These connectors have no value. If you want, you can assign like a part number for their value, but you can generally ignore these. So if it's okay, you can just approve them all. And then you have no more warnings, no more errors, and you're good. So then you can just save your board there, and ERC hasn't found any issues. Again, it's not going to tell you, hey, this 5 volts is supposed to be connected to 3.3 volts. It's a very rough check just because Eagle doesn't know exactly what you want. So once you've reviewed your board, or reviewed your schematic looks good, is what you mean. Basically, your schematic is done at that point. You can add some things to help make it look a bit better. So organizing your circuits, like I already mentioned, splitting the design up into multiple pages by like, these are the voltage regulators, these are the connectors, these are the chips, whatever, however you want to organize it. Splitting it up makes it a lot easier to see. Like, okay, this page is good. I know this page, everything on here is perfect. And you can just say, that page, I've done reviewing it, it's all good. And then you focus on the other ones, stuff like that. You can add frames like I showed you. It like restricts you to a physical size. So when you print it out, it's nice. It helps you get an idea of where you are instead of just being in an infinite white space. And again, like that helps when you're printing, it'll make it work and be visible when you print it instead of it scaling to be infinitesimally small or large. And when you're working with circuits on the same page, you can use lines to divide them. So I can show you an example of this a little bit later after this slide. And then you can add text to your schematic, which will like say, okay, this is the 5 volt regulator, this is the 3 volt regulator, this is the PWM driver, just like something on there that says, what is this circuit doing? Why is it there? What does it do? And when you're making connections, use net labels as much as you can. Like I mentioned, using the little like cross-reference thing that Kurt was explaining, or something like that, just makes it a lot easier to see what's going on because you can see, okay, on this sheet, it's connected to this thing, rather than having a trace like squiggle all the way around your page, a bunch of traces crisscrossing, and it makes it really hard to see what's going on. So naming things is a lot better, in my opinion, than just drawing wires everywhere. Except for like if you're connecting a pin to ground, or if you're shorting 2 pins together, like just draw a line. You don't need to name it or anything like that. But if you're going to connect like one thing to another thing, like a whole integrated circuit to another integrated circuit, it's a lot easier to just name it rather than have a ton of traces going back and forth. And then when you're putting things in your schematic, try to organize things as much as you can so that everything like lines up nicely and it's not at weird angles or it's not like misaligned or anything. And I can show you what a bad example of that would be in a second as well. And then make sure you use these intersection or junction dots to connect nets. So you saw if you like draw a line across a bunch of nets, it doesn't automatically connect them, even though it looks like they should be. So make sure you use these junctions to like connect a bunch of wires that are like coming into an intersection together if you want them connected. And if they're not supposed to be connected, probably just give them a bit of extra space, make it really clear that it's not supposed to be connected so it's understandable when you like look at the circuit or glance at it. And to that note, avoid crossing wires if you can, but if you can't, just try not to make like sharp turns right next to each other, because that'll kind of be hard to follow which wires are going where. If you have a big line of circuit, big line of wires like that, it's really easy to see which one came in and went out where you didn't, like they didn't do like a 90-degree bend at the same point. Just keeping things as clear as possible is all that schematics really need to be. Make it easy to take a glance at it and see what it's supposed to do. So if we go, I can show you an example of adding like text to your circuit to label what is going on in each piece. We'll just go with this one for now. So actually, while that's loading, we'll jump ahead a bit. So we'll I'll show you like, never mind. We'll just wait for Eagle to load. But yeah, so show you the text thing. So where is it going to load? Okay. Okay. So actually, never mind. I didn't mean to pull this one. I have too many PCB files on my computer. Sure, we'll look at my senior design project. I think this version of schematic might be fine. So yeah, so this is an example of what I mean. So I have big red text saying like this block is the serial adapter for communicating over USB to a computer. This is the microcontroller. So you clearly can like at a glance figure out like what's on this page. Oh, it's the USB port, display, power switch, stuff like that. So big labels make it really easy to figure out what's where, especially if you're in a schematic PDF view or something like that. You can just scroll through and figure out where everything is. And to the same note, organizing circuits, if they're on the same page, just add a line to divide them. Zoom overlay is annoying, but you can see I have this dashed line here saying like this side is for the microcontroller, this is where all the USB serial adapter is. So it kind of splits each bit off into their own area. So it's clear what is for what label. It's like all of this is the battery charger BMS, this is the battery cell, this is the 3-volt regulator, etc. And you can see I use the same frames for this one. You can see down here, I've named the document. Here's the project name. That's when it was generated, all that sort of stuff. And you can see that they're also on multiple pages for each different sub-circuit. Every certain purpose it serves has its own page. And again, use net labels as much as you can. I've basically connected as much as I can with just net labels. You can see there's no wires that cross these lines, but the names connect everywhere. So you have USB coming in from 1.1A. Here's sheet 1, 1.1A. Here's USB in smaller text for some reason. And again, that's connected on the USB port over here on page 2. So you can see I'm using these net names to connect as much as I can rather than having wires just go everywhere and have everything all on one infinitely large page. And then make sure things are aligned. So if you don't align things, like it can be really weird. Like just please don't do something like this. This is just terrifying. Like this is disgusting. Don't do this, please. Like it all means exactly the same thing to Eagle. It's just impossible for a person to look at it and figure out, well, where does SCL get connected to? Modern art, yes, yes. So electrically, this is exactly the same. If we run ERC check, it'll say you're perfectly fine. Yeah, you can see down the bottom, 7 approved, errors warning. So it's nothing new. This is fine to Eagle, but it's just terrible for a person to read. So like if you can line things up so like the pin goes in a straight wire as much as you can, short little gaps is really nice. So again, like just align things up, please. It makes it so much easier to see what's going on and make short wires and traces. And then in terms of intersections, you guys saw the thing when I made a trace here, it didn't add these bubbles automatically, even if I wanted them to. So you can use the junction tool to pin these. So these are all connected to each other. So they're all connected to ground. And so at this point, basically the schematic is done. It's been reviewed. It looks good. Looks good in terms of the development board we're basing it on. Looks good for the schematic. And it looks good for application circuit, everything. So we followed the schematic tips. It looks pretty decent now that the disgusting part was fixed with the crisscrossing wires at like 30-degree angles and things. So that's pretty much this whole schematic is done. And then next would be to move on to the board design. So once you've done the schematic, you'd click this button up here to actually start making the board. If it doesn't exist, it'll make one. We're not going to get into it, but basically here's all the footprints of everything we need. You can move them around, but we'll get into that next time on the second PCB workshop, putting these all around. And you can see all these schematic symbols we had turned into actual footprints. And you can see all these nets are these little wires that are saying, hey, this needs to be connected. So that's what the physical meaning of these wires is. They turn into those green wires in the board layout. So at this point, does anyone have any questions? Please, I hope somebody has some questions because I went over an insane amount of stuff. So please unmute or post in chat or anything, or message me after, whatever you want to do. But if anyone could ask questions now, it'd be great for the recording so people can get their questions answered, because this is a very complicated topic. It's not trivial to design a schematic for a PCB. So please ask questions.
I got a question.
Okay.
So let's say we join a team, one team of the iRobotics, and we try to work on a project. And we have to design a printed board for that. Where do we start? How would the whole process work? How would it look like? What kind of knowledge do we need to know before we handle that? We can handle the responsibility and things like that.
Yeah, so that's a good question. When, like, a lot of our teams are structured in a way that anybody can really start. Like, there's nothing really technical about any of the work that this workshop showed. Like, it's fairly straightforward, especially if you're just like remaking a module of somebody else, or you're making a circuit that you understand is basically the only limitation. If you want to learn how to make like an amplifier for audio, just Google it, learn it yourself. You don't have to learn it in a class or anything, and you can do it, or base it off of an application circuit, or base it off of a development board, anything like that. There's not really like you must know this much stuff before we'll allow you to build a PCB or design a PCB. Like, if you want to, like, just talk to your captain. I'm sure they'd be happy to help get that rolling, because we're a robotics club. Electronics is kind of a huge thing we do, especially on the control side here. So, like, I'd really encourage anyone to try to do some sort of PCB if they can, even if it is just to like design it. You don't need to manufacture it, just to kind of figure out how it works, because starting off, Eagle is a little bit weird to learn how to use, but you'll get a lot more accustomed to how it works as you use it more. So even just like going through and making a simple design like this PWM driver is really helpful for getting an understanding of how to do it. And then you can actually do it for a robot if you wanted to. Just really, there's no minimum knowledge you have to know or any class you have to have taken. It's just whatever circuit you feel like you can make, just go for it, basically. Like, with whatever resources you can find, working with a couple partners on the project, or off of an application circuit or something like that.
All right, thank you.
No problem. Anyone else have any questions? Want to see any other PCBs? I have plenty of them. Oh, fucking course, more PCBs. Okay, Kurt, I can oblige. I don't know if my computer will enjoy it, but, you know, 10 tabs of Eagle is fine. But anyone else have any other questions, like suggestions for boards or anything you want to talk about PCBs wise or anything?
Well, while you're opening like another example, I was just curious, was there any classes that you took that you think gave you a lot of advantage in terms of developing those PCBs, or do you think it's purely Google, YouTube, that's it?
Yeah, so I don't think there's necessarily like a class that will work to teach you PCBs. They're like ECE in general teaches you more like the electrical design, kind of the schematic side. But yeah, and I'll have an attendance link at the end. But yeah, so like there's not really a great class because you don't really do stuff with PCBs in your classes until like you're making some sort of project. Like for senior design, you'd make a PCB, but all of the classes before that use breadboards just because you're developing it. You're not really making a final product. So most of it is like self-taught, or you learn it from like working on projects like for iRobotics or an RSO or something like that. There's not really like a PCB class or anything you can take as far as I'm aware.
Gotcha, thank you.
Yeah, so this is one board. It's quite complicated, but it's a battery management system, battery charger for a 6S lithium-ion battery. It has a lot of things in it, but really it's not any more complicated than the schematic that I showed you or we made. So even if we switch back to the schematic, if my computer will stop trying to die. So like you can see the same thing where I have the frames, I have the components, I've got tons of labels on everything, like kind of well-aligned components, stuff like that. There's nothing really complicated. A lot of this is from application circuits for the chip. I can pull that up actually to give you an example of one for a TI chip, because TI is very good for documentation, as Kurt can attest to. But yeah, so they give you like a little simplified schematic. That's not the full application circuit. But here's application information, typical applications. We'll just go to that. And here's the schematic. So literally you can just copy this, tweak some of the values depending on your application. Like, so this is for these parameters. You can tweak them to give you all the equations. You can just plug in numbers and they'll give you the right values you should use for all of this. And basically that just turned into this, and these sheets is all just recreating that schematic. And then once you've named it all, you can just put it in, lay it all out, add all wires. That'll all be in the next workshop. I'll show you guys how to do routing, layout, all that sort of stuff to make it all physically connected. And then it'll end up looking something like that-ish, which turned out pretty well, I do say so myself. But yeah, so like Kurt mentioned, they'll give you a full layout. Sometimes I don't know if this one does. There's the footprint for it that you could use if you want to make it yourself, or you can just use the one that DigiKey has already made. My computer is not having a good time running Zoom this many instances of Eagle, but we'll just make it keep going. So there's a little bit of stuff. Yeah, actually, here's all of the layout guidelines. This is what they recommend you do for your PCB to implement them as best as possible. They do a bunch of really good stuff. So TI chips work really well for initial layouts and stuff. They're very well documented. This document is like 100 pages long or something. So really good information there. So yeah, if you guys have any other questions, feel free to let me know, like more PCBs if you guys really want. But again, message me on Discord, send me an email, anything like that. And there is the PCB worksheet, or not worksheet, this is not a class. There's the attendance link. I think the forum is open. Yep. So feel free to fill that out to get your membership point for coming today. Thank you guys all for participating. Again, please let me know if you have any questions. I'll be sending out the recording and then the schematic file we designed today in the newsletter next Monday, Tuesday time, something like that. And again, I'll hang around a little bit. If anyone has any questions, wants to look at other PCBs, ask what the PCBs do, because they're kind of just big McDonald's colored blocks right now. This one is less. No problem. I'm glad you guys got to come out. Okay.
Can I ask another question?
Yeah, of course.
More close to the actual PCBs.
Mm-hmm.
So I downloaded Eagle before, and I watched like a couple of tutorials about it, but I never like digged in deep into it. But I'm still thinking about sometimes there's like 2 layers of ground, and I never understood why. Like, why would you have 2 layers of ground? How does it help us in our design?
Yeah, so Chrome, or all these overlays from Zoom cluttering my screen, but yeah, so I think what you're talking about is if you have like a 4-layer board and then you have like the inside layers are ground. Is that what you're trying to get at? So like.
Well, okay, but yeah, probably. Yeah, I think so.
Yeah, so this is what like a 4-layer board looks like if you like cut it down flat. So you have your top layer, you have an inner layer, another inner layer, and a bottom layer. And so a lot of times what they do is they have these layers that are just fully ground. And so what that's supposed to do is help reduce like noise, because all these wires are so close together. If you have like switching frequencies from like a voltage regulator or from a PWM signal, it might generate noise, and that might cause a voltage in the other wires. Like if you're measuring a voltage that's like 3 millivolts, 5 millivolts or something like that for a current shunt, the ground is supposed to be in between, and it's supposed to help reduce the noise from like switching signals from your like sensitive analog voltages. It's not like strictly required for a lot of things. It's like more of a best practice sort of thing, where like ideally you'd have something like a 16-layer board and you'd have like ground on one side, ground on the other side, and then in the middle you'd have your analog signals. You're basically like making a Faraday cage around your analog signals to protect them from any noise, but generally you can get away with like not doing that. You can kind of see if I turn on this layer. So like all of this yellow is ground, or the main fill, like not the wires here, but everything else is ground. And that's serves kind of the same purpose. You can see there's a bunch of like holes in it where like these gray areas aren't ground. The little wires here aren't ground. So it acts kind of well to protect against like noise from switching signals or something like that, but it also serves to allow like extra ways for ground current to flow. So when you have, for example, like, let me show you an actual example of how it would be used. So here we have PVDD, which is like our battery voltage. It goes through a MOSFET to this, and then it goes to here, which goes out from here through a MOSFET to this area over here, which is like SLC. And you can see they go all the way down here. And then if we go to the bottom layer, you can see all of this is ground. And if we look at the bottom, it might look a bit better in this view. So you can see like this thing R7 is a shunt resistor. So it just it allows it to go through a bunch of extra paths to ground. So if by default, like you'd have this one big wire here, it'd have like one trace to ground. But if you have this internal layer that's ground too, you then have two traces to ground, which will help reduce the resistance, make the power flow more easily with less heat. And it just like, it's redundancy, it helps reduce noise, it helps a lot of things just to give it a bunch of different additional paths to ground. So like the same applies for all of the microcontroller stuff. Like this references ground all over the place. And if you have one trace to ground, if that one gets noisy or if that one gets broken, suddenly everything breaks. Whereas if you have a bunch of these other paths to ground, nothing changes. It's basically the same, even if one trace gets like cut or something like that. But does that kind of answer your question?
Yeah, and I right away have another one, if it's okay.
Yeah, sure.
That's, as I remember, you mentioned like the Faraday cage and things like that. So
yeah,
and I know when you design a physical circuit, there's things like impedance from the wires, and you need to check on that, and like little physical details that they're not like ideal approximations.
Yeah.
When you design a PCB, is a PCB designed in a way that it's set up already in a way that you don't have to really adjust for those, or is there anything that you need to check as an engineer that's really kind of might not be ideal there?
Yeah, that's a really good question. So generally, you don't need to worry about the non-idealness. So like if you're looking at the schematic, let me try to find a good example of something. So like, sure. So like this trace here, that is like the signal that controls the MOSFET, that doesn't really care if there's any noise or if it's a little bit of extra resistance. Like there's already a 4.7 ohm resistor in there, which does some things with ringing and reducing current spikes. But basically, if this turns into a 4.8 ohm resistor because of the traces when you actually manufacture it, like it's not a big deal. So generally, it doesn't matter very much. Now, where it does matter is over here. So these shunt resistors are 500 microohms. And when you have current flowing through them, there's a voltage across them. And when you're trying to measure these voltages, you're going to get like 5 millivolts of voltage across them, maybe, if you're lucky and pulling a lot of current. And so those signals can really easily be affected if there's any noise or something going nearby. So in that case, you would be a little bit concerned about the switching, if there's any noise in your circuit, and if you don't have them like surrounded in some sort of Faraday cage or something like that, you don't need to worry about the like resistance because you're measuring a voltage, you're not measuring current really. So, I mean, I kind of, but you're measuring on the order of like nanoamps of current. So the resistance being a little bit higher than ideal doesn't really affect voltage measurements when you're measuring it this way. So generally, you don't need to worry about the resistance of the traces, not to mention if you actually measure any of these traces, they're on the order of milliohms at most, even for like really long ones. But I can show you, for example, for measuring those, like the voltage across this sense resistor, this SLB trace. I look for the signal. I think I can highlight it. Yeah. So okay. Yeah. So here you can see this SLC trace. Actually, that's not a great one. Let me go off of SLB, I think is a bit better. But yeah, so we have this trace is going to this SLB, which is what we're sensing. This is the voltage. And then it goes like in a short path to the chip with ground on either side. There's some other signals. So like for measuring the temperature is another one where you're measuring more current, so it's a little bit more sensitive. So if we look at this temp trace here, you can see this is a lot longer, so it'd be a lot more sensitive to noise or anything. And then you can see the way that this is set up is I have really these traces that are right next to each other. So this is called a differential pair. Basically, what it's supposed to do is any noise that affects one side affects the other trace because they're as close together as you can get them. And so ideally it cancels out on both sides because they both get affected by noise in the same way. So that's one thing you can do if you're going through like a noisy environment, like all of this is switching at a couple kilohertz and you have these analog signals right next to it. And so like one thing, you're putting them next to each other. Another thing is there's this layer in between. So the ground helps. It's not perfect because there's these holes in it, like I mentioned, but there is a ground between them. So it helps stop some of the noise. And so, yeah, there is some instances where you should be concerned about it, but a lot of the stuff you don't need to worry about it, especially if you're working with like digital signals, because if it's 3.3 volts or 3.2 volts or like 2.8 volts, it's all the same. So if you're worried about resistances for digital stuff, you don't really need to be. So for a lot of stuff, you can ignore it and it'll probably work out fine. A lot of these standards are built with being in worst case conditions in mind. So if you're running USB on your traces and it's going right past these huge high current switching MOSFETs, it'll probably be fine just because of the way they defined the standard to make it so that it can handle that. So you don't need to worry about it too much, especially if it's for like a personal project. If you're making something for NASA, you might want to be concerned about it, but for like a one-off sort of robot sort thing, it's not something to be too concerned about. That was a really good question, though. I like that.
Well, what if it's not NASA? What if it's iRobotics? And can you give us, maybe you had a, like how would ever happen when the circuit should work perfect in theory, but it doesn't, and there was something there?
Well, I mean, of course it always works perfectly in theory until I get the board and I find out, oh, I forgot something or I misread the data sheet. But like in terms of having issues with like the resistance of the wires or capacitance or something like that, I've never had issues. Like originally when I started off putting USB on my boards, I was like, okay, like what is the impedance of this? I have to make sure that the trace distance width is all perfect for USB. And I was really concerned about it. And it worked fine then. And then I was like, well, I don't really have enough space. So I'm just going to kind of use smaller wires and kind of ignore some of the rules for USB. And then they worked perfectly fine too, because all these standards are designed to be able to work in pretty much any conditions, especially if you're working with like not bleeding edge stuff. If you're working with like 10 gigabits per second USB-C, you should probably adhere to the guidelines, but for basic stuff, especially if you're working in the order of like megahertz, it's not really a huge issue to take liberty with your PCB design, especially for like robotics and stuff. You're not doing anything on bleeding edge with like gigabits per second of data moving around anywhere. Yeah.
So you can send this circuit to space.
Honestly, most of mine would probably be fine if they went in space. It's just I have a lot of them and I need to write code for a lot of them to make them work still. I have a habit of making PCBs and then making another PCB before I finish the code for a different one. Like this one, I have it here, but I don't have the code written for it yet. I have some code, just not all of it. And then I started working on other projects because I have an issue with taking on too many projects at once. But yeah, so chat. Too real for Kurt. Yeah. Yep. I've got the exact same issue. Anyone else have any questions? Want to see anything else? I mean, I can give you a preview of next workshop a bit. Not too much because I still need material for the next workshop, but. Okay, well, if nobody has any other questions, I think probably good. We've been going for quite a while now, so don't want the recording to be too terribly long. But thank you guys all for coming. Again, if you have any questions after the fact about the files or anything, just send me a message in Discord, send me an email. It's in the slides. They'll be sent out with the newsletter. So thank you all.